Hi, everybody. I came across a board game the other day, and it's about pirates, and it has this this die in it. It's got a die with a 1, a 2, a 3, and a 4, but because it's a pirate game, it's got a skull and crossbones on this side and a skull and crossbones on another side. So I was wondering, if I have to roll this die in this game, what's the probability that I get a skull and crossbones? Well, that question's not so hard to answer. There's 2 skull and crossbones out of 6 sides. So 2 out of 6 is 1/3. Probability of getting a skull is 1/3. Probability of not getting a skull would therefore be 2/3. But what if I had to roll this die like 4 times? And I want to know what's the probability that I get 3 skulls, or no skulls, or just 1 skull. So it turns out the answer to this problem involves what's known as the binomial distribution in statistics. And so that's what I want to talk about. We're going to learn about the binomial distribution, and we'll go through this example, and then we'll go through an example where we apply it to real life. And so let's go down below and see how this works. Okay, so I want to roll this die, say, 4 times. So let's say n equals 4. And I know the probability of success. The success is getting a skull and crossbones. I'm a pirate after all, so that's the success for me. And we talked about the probability of that is 1/3. Okay, so what I want to do is talk about the probabilities of getting a certain number of successes. So let's talk about the probability of getting 0 successes. What would that be? Well, let's think about it. Let's just think about how can that happen. Well, to get 0 successes must mean I've gotten, since I rolled it 4 times, I must have gotten 4 failures. Right? So I must have had failure, 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 failure. So that's what I'm looking at. Well, what is the probability of 4 failures? Well, each failure occurs with probability 2/3. The success is 1/3, so the failure must be 2/3. So to compute this, I'm going to take 2/3 times 2/3 times 2/3 times 2/3. 4 failures in a row. So this probability you can just write as 2/3 to the 4th power. That's the probability of getting no successes. I got 4 failures. What about the probability of getting 1 success, exactly 1 success? What is that going to be? Well, let's list out the possibilities. I could get success followed by 3 failures. That's one possibility, but there's another one. I could have gotten a failure followed by a success followed by 2 failures, or I could get failure, failure, success, failure, or I could get failure, 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 success. There's actually 4 ways you can get exactly 1 success. What's the probability of any one of these? Well, take the first one. The probability of a success is 1/3. The probability of a failure is 2/3. And we got that 3 times. So 2/3 times 2/3 times 2/3. And what about the next one? Well, here my failure was first, so 2/3, followed by my success, 1/3, followed by 2 failures, 2/3, 2/3. What about this one? It's failure, failure, success, failure. 2/3, 2/3, 1/3, 2/3. What about the last one? It's failure, 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 success. So 2/3, 2/3, 2/3, 1/3. When I multiply this out, I get 1/3 times 2/3 cubed. Or 1/3 to the 1st power, 2/3 to the 3rd power. And that's the same thing I get here. When you multiply, you can reorder the order in which you multiply. So this is the same thing. And so is this, and so is this. And so to get exactly 1 success, I either did this, or this, or this, or this. And when we do ors, we add. So what we're going to do is, to get the actual probability of getting 1, we have to add all these together, or it's the same thing as multiplying this by 4. So that's a formula for getting the probability of exactly one success. What about the probability of exactly two successes? How would that pan out? Well, how can that happen? I could get success, success, failure, failure. And let's just move this second success around. So I can get success, failure, success, failure. Or I could put the success at the end. Success, failure, failure, success. Or I could get, let's move this first success over. So put that here like this, failure, success, success, failure. Or we could do failure, success, failure, success. And let's move the success to the third position. I could get failure, failure, success, success. And that's all the possibilities. That's all the different ways that I could get 2 successes in 4 rolls of a die. So let's look at the probabilities here. Success, success, that's 1/3 times 1/3. Failure, failure, 2/3 times 2/3. And as I go through here, you'll see I get the same numbers just in a different order, right? So success, failure, success, failure. To the next one, success, failure, failure, success. And each time you do this, you get the same 4 numbers. They're in different order, but that doesn't matter. You're getting the same thing. So let's just compute the first one, and we'll multiply it by 6, right? So this is 1/3 squared, 2/3 squared, because there's 2 1/3 and there's 2 2/3. And how many of these are there? There's 6 of them. Okay, so that's the probability of getting exactly 2 successes. Let's keep going. Let's do the probability of getting 3 successes. Probability of getting 3 successes. Well, how can that happen? I could get success, 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 failure, success, success, failure, success, success, failure, success, success, or failure, success, success, success. So one of these. What are these probabilities? Well, I got 1/3, 1/3, 1/3, 2/3. And I think you can tell from above, all of these are going to be the same, right? I just have the same numbers in a different order. So what do I have? I have 1/3 cubed times 2/3 to the first power. 1/3 cubed, 2/3 to the first power. And I have 4 of them. So that's my probability of getting exactly 3 successes. Finally, the last one will be the probability of 4 successes in 4 rolls of a die. So that's success, 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 success. Well, that's 1/3 times 1/3 times 1/3 times 1/3. And there's only one way that can happen. I can't write down anything other than this for 4 successes in a row. So it's just 1/3 to the 4th power. All right, so we've computed all these different possibilities. We computed the probability of 0 through 4 successes. Now what I want to do, though, is I want to look at these and see if we can see a formula. We can kind of recognize what the formula would be so that we can do this in a more general setting. Well, let's see. These numbers, I think, the exponents, you can kind of see what these might correspond to. If we look at these exponents, notice that they always add to 4. The exponents are always adding to 4. And that makes sense because the exponents are accounting for the probability of each roll. And there are 4 rolls. So the exponent should add to 4. The exponent that's on the P, the probability of success, is the number of successes. So if I had 1 success, I'm going to have an exponent 1 on that probability. And then the other exponent is just the number that has to add to that to get n, in this case 4, and then that's the probability of a failure. Now where does this coefficient come from? Well, that coefficient is counting the number of ways I can distribute this many successes among 4 trials. And if you recall, we talked about this in class before. There's a way to measure this, the number of ways you can choose k things from n things. And that's called combinations. So let me use this space up here. What we're recognizing is that the probability of getting k successes is going to be equal to some number times the probability of a success raised to the power k, right? Just like we had here, the probability of one success was this probability raised to the number k. And then the probability of a failure, and the probability of failure is always 1 minus p, that's the opposite of a success. And then this number is actually what you'd have to add to this number to get n. So it's n minus k. If you add these together, you get n, the number of trials. And the number that goes here is what they call n choose k. N choose k, also written sometimes like this, has a formula. It's n factorial divided by n minus k factorial times k factorial. And that's something we learned from when we discussed counting in statistics. So this is the formula for computing binomial probabilities. Okay, so what I want to do is I want to talk a little bit more about this and then apply it to a more general problem. And we'll also see how to use technology to do this in this problem, right? So let's take a look here at if I can find my problem here. Okay, so it says that a health insurance company found that 70% of the people they insure stay below their deductible in any given year. Suppose the insurance company, the insurance accounts for 8 people in 2019 are randomly selected. Find the probability that 6 of them stayed below the insurance deductible. So let's think about this like we were thinking about the other problem. Instead of rolling dice, we're choosing people. And instead of rolling a success, we're finding a person who stayed below their insurance deductible. And we know the probability of that success is 70%. So we really have all that information here. We have the p is 0.7. The number of trials, n, is 8. And we're asking for the probability of exactly 6. Okay, so let's go down below and write this down. Okay, so our n is 8. We're choosing 8 people. The probability of a success is 0.7. And we're looking for the probability that exactly 6, we had exactly 6 successes, exactly 6 people stayed below their deductible. Well, if we go back to our formula right here, this is it. It's going to be n choose k, so 8 choose 6. And that's just using this formula. P to the 6, there's 6 successes, so multiply the probability of success by itself 6 times. And then probability of failure is 1 minus p, so that's 0.3. These have to add to 1, right? And these numbers have to add to 8, right? So that has to be a 2. Or in other words, you take 8 minus 6, and you get 2. Okay, so that's what we have to compute here. And if you use a calculator, you can get the answer. What I'm going to do is actually show you how to do it using StatCrunch. Okay, so this is what you'd do if you didn't have StatCrunch. You'd go ahead and compute this thing out. But let's go ahead and use StatCrunch and see what it tells us. If I can find it here. So you're going to log into StatCrunch, and you're going to come to the data matrix. And what we're going to do is we're going to go to Stat, Calculators, and Binomial. We're using the Binomial Distribution here. So go ahead and click that. And here's what we see. We were told that we had 8 trials. The probability of success was 0.7. And we want to know the probability of getting exactly 6. So not less than or equal to, but exactly. So we put an equals to sign here. Now here, what it's showing us is actually the distribution. The heights of these bars, to these bars above, there's actually one above, I don't know why it's not going to 0, but you can see a bar over here above 1. There's a bar above 2, 3, 4, 5, 6, 7, and 8. And the heights of these bars is the probability of getting that result. So what we're looking for is actually just the height of this bar right here, the probability of getting exactly 6. Looks like it highlighted it in red. It's a rather thin bar. I wish they made them thicker. But we can see the exact height. It's written right here. 0.296, if I rounded, 0.2965. So that's what I would get if I was to carry out that computation I showed you on the paper, 0.2965. All right, so let's go to the next question. The next question was, what's the probability that less than 6 stayed below their insurance deductible? Okay, well, if you were to do this by hand, this would be somewhat tedious, right? Because what you need, we've learned is the formula for finding exactly 6. So less than 6 means it's either exactly 0, or 1, or 2, or 3, or 4, or 5. So you'd have to use that formula for each one of those and add them all together. And that would take a while. That would be a lot of work. Although there is a quicker way to do it, because the opposite of less than 6 is greater than or equal to 6. So you could really just do the probability of 6, 7, or 8, add those together, and subtract from 1. But that's still going to be a lot of computations. Nice thing that we have here, though, is that StatCrunch can do, it's a computer, so of course it can do this all very quickly. So what are we looking at? We're looking for less than 6. So all I have to do is change this to a less than sign. And there's my answer, 0.4482. So that would be the answer to part B, 0.4482. And finally, the last problem says at least 3 of them stayed below the insurance deductible. Well, at least 3. So that means 3 or more, or greater than or equal to 3. So what I'll do is I'll go to StatCrunch, and I'll put 3 and a greater than or equal to. So it's highlighted in red, all the bars from 3 on up. And we see the probability of getting at least 3 successes is 0.9887. So that's the answer for part C.